Picture this. You're on a plane, halfway across the Atlantic. Someone in row 17 reaches for their backpack, and suddenly there's smoke, sparks, and then flames shooting out of the side pocket. People panic. Flight attendants rush down the aisle with a special fireproof bag, and the culprit? A small, ordinary-looking battery, the same type inside your phone, laptop, and earbuds. Now here's the twist. This little metal cylinder that just caused chaos is also one of the greatest inventions of the modern world. It powers billions of devices, from satellites to scooters. Without it, we wouldn't have smartphones, laptops, or electric cars. But it's also dangerous enough that airlines literally carry equipment on board just to contain it if it misbehaves. So, how did something this risky, this unstable, become the foundation of our technological age? And why, after decades of searching, don't we have something better? To answer that, we have to rewind back to the 18th century, when a twitching frog leg started a scientific revolution. The year is 1780. Italian scientist Luigi Galvani is dissecting a frog. He hangs one leg on a brass hook and touches it with a steel scalpel. To his surprise, the muscle contracts violently, almost like the leg has come back to life. He's stunned. Did he just discover the secret spark of living creatures? Galvani calls it animal electricity, but not everyone is convinced. His rival, Alessandro Volta, thinks the twitch has nothing to do with some mystical life force. Instead, Volta argues, the electricity comes from the contact of two different metals, with the salty fluids in the frog acting as a conductor. To prove his point, Volta stacks alternating discs of zinc and copper separated by brine-soaked cloth. When he connects wires, a steady current flows. The first battery is born. This early voltaic pile produced less than 1 volt, but it changed everything. Suddenly, scientists had a continuous source of electricity instead of relying on static sparks. The world had entered the age of electrochemistry, and the basic idea anode, cathode, and electrolyte remains the blueprint for every battery today. Even the lithium-ion cell in your phone owes its ancestry to that twitching frog. Jump ahead nearly 2 centuries. It's the 1970s, and the world faces an energy nightmare. The Yom Kippur War breaks out in the Middle East, in retaliation for U.S. support of Israel. Arab oil producers cut off supplies. Overnight, crude oil prices double. Gas stations in America run dry. Drivers wait in lines stretching for blocks. Politicians lower the national speed limit to 55 miles per hour just to conserve fuel. For Exxon, then the largest oil company in the world, the crisis is a wake-up call. What if oil really does run out? They need alternatives, and one of the strangest paths they pursue is batteries. At an Exxon lab in New Jersey, a 32-year-old British chemist named Stanley Whittingham is studying how different materials can store and release energy. He's not thinking about cars or phones, he's just curious. But when executives hear about his work, they give him a green light. His only rule, he later joked, was that he could research anything as long as it did not involve petroleum. Whittingham focuses on a class of materials called transition metal dichalcogenides. One, titanium disulfide, is especially promising. Its layered structure can host ions slipping in between, like books sliding onto a shelf. He pairs it with a highly reactive anode, pure lithium metal. The result? A rechargeable battery that delivers 2.4 volts, nearly double what conventional water-based cells could do. Suddenly, Whittingham has something the world has never seen before: a lightweight, high-energy rechargeable cell. Exactly the kind of breakthrough that could power portable electronics or even revive the long-forgotten electric car. But there's a catch. And it's a fiery one. Lithium is light, small, and desperate to give up its outer electron. That's what makes it so powerful in a battery. But it's also dangerously unstable. When Whittingham's prototype is charged too quickly, lithium doesn't plate smoothly onto the electrode. Instead, it grows into needle-like structures called dendrites. Under a microscope, dendrites look like tiny metallic trees, but they're anything but beautiful. They can pierce through the separator, basically the thin plastic sheet meant to keep the electrodes apart, and suddenly connect the anode and cathode directly. That creates a short circuit, current surges, heat skyrockets, and in a blink, the cell bursts into flames. Exxon's labs dealt with so many fires that local firefighters grew tired of responding. They threatened to start charging the company for the special chemicals needed to extinguish burning lithium. Imagine being the scientist whose experiments keep setting off alarms week after week. Still, for a while, Exxon pushed ahead. The oil crisis had given the project urgency, but when prices fell back down and the panic subsided, enthusiasm evaporated. By the mid-70s, Exxon shut the program down. Whittingham published his design in 1976, but without funding or momentum, the world's first lithium battery revolution fizzled out before it began. Across the Atlantic, however, Whittingham's work caught the eye of another scientist, John B. Goodenough, an American physicist leading a solid-state chemistry group at Oxford University, read the paper and spotted something. The cathode was holding back the voltage. Goodenough suspected that a transition metal oxide would perform better than Whittingham's sulfide. He tested lithium cobalt oxide, and the results were spectacular. The voltage jumped from 2.4 volts to nearly 4 volts per cell. For batteries, that's like leaping from a horse-drawn carriage to a sports car overnight. Even more surprising, lithium cobalt oxide already contained lithium ions in its structure. That meant you could, in theory, build a battery without using dangerous metallic lithium at all. The ions could move in and out of the cathode crystal instead. Goodenough was ecstatic. He believed this chemistry could revolutionize energy storage. But when he pitched the idea to companies in the US, the UK, and Europe, no one bit. Maybe the idea seemed too risky. Maybe bureaucracy slowed things down. In any case, his breakthrough was patented in 1981, but without commercial interest, it gathered dust. For the second time, the lithium battery revolution stalled. Meanwhile, in Japan, a young chemist named Akira Yoshino was on a mission. He wanted to build a rechargeable battery that avoided the hazards of metallic lithium. He experimented with a conductive plastic called polyacetylene. It could host lithium ions, but the density was too low. The batteries were weak. Then, while cleaning his office at the end of 1982, Yoshino stumbled across Goodenough's paper on lithium cobalt oxide. That was the missing piece. The cathode already contained lithium. All he needed was a stable anode that could host the ions safely. After testing countless materials, Yoshino turned to carbon, specifically a new form of carbon fiber developed within his company. Its crystalline structure could repeatedly absorb and release lithium ions without breaking down. And unlike metallic lithium, it didn't form dangerous dendrites. To prove the difference, Yoshino staged a dramatic test. He placed a cell with lithium metal into an explosive safety rig and dropped a heavy iron rod onto it. Boom. Violent explosion. Then he repeated the test with his new carbon anode cell. Same iron rod, same setup. This time, nothing, just silence, safe and stable. In that moment, Yoshino realized he had solved the puzzle. The lithium-ion battery was born. Yoshino's employer, Asahi Chemical, wasn't a battery maker, but in 1986, a determined executive partnered with Sony to bring the design to life. Sony engineers swapped in graphite as the anode, which could intercalate lithium ions even better than Yoshino's carbon fiber. In 1991, Sony launched the first commercial lithium-ion battery inside the Handycam camcorder. It was compact, powerful, and rechargeable. Competitors like Panasonic and Sanyo rushed to follow. Suddenly, lithium-ion was everywhere. Phones, laptops, CD players. By the mid-90s, ads bragged about devices running 8 hours straight on a single charge. One Dell magazine ad was 8 pages long, with each page boasting 1 more hour of runtime. Lithium-ion had become a selling point in itself. Consumers didn't just want gadgets. They wanted gadgets with lithium-ion inside. Think about it. Without these batteries, your smartphone would be a brick, your laptop would weigh 5 kilograms, and electric cars would still be science fiction. From 1991 to today, the price of lithium-ion cells has plummeted by 99%, from nearly $9,000 per kilowatt-hour to just about 100. At the same time, energy density has doubled, and cycle life, how many times a battery can be charged and discharged, has soared. This transformation revived the electric car. It enabled renewable energy storage. It shrank cameras, powered satellites, and made wireless everything possible. In 2019, Whittingham, Goodenough, and Yoshino finally received the Nobel Prize in Chemistry for an invention that, in the committee's words, revolutionized our way of life. Good enough, at 97, became the oldest Nobel laureate in history. But as with every great leap, there's a dark side. Every week in the United States, at least one lithium-ion battery incident happens on an airplane. That's why flight attendants now carry special containment bags made of non-flammable material. If a phone catches fire, they seal it inside and prepare for an emergency landing. The science of failure is sobering. At around 80 degrees Celsius, the protective SEI layer on the anode starts to break down. More reactions release more heat. At about 130 degrees, the separator melts. The electrodes touch. A short circuit follows. The cathode decomposes, releasing oxygen. And now, the battery feeds its own fire with fuel, oxidizer, and heat all inside the same little package. It's not actually the lithium that burns modern cells, contain very little of it, but everything else. Solvents, binders, and oxides. That's why battery fires are so hard to extinguish. Water can cool them, but suffocating them doesn't work, because they don't need external oxygen. The odds of failure are tiny, about 1 in a million cells. But with billions of batteries in circulation, the math guarantees incidents. From laptops on planes to Teslas on highways, we've all seen the headlines. It's rare, but it's real. Beyond safety, there's the question of where these materials come from. Lithium is rare, only 20 parts per million of Earth's crust. Extracting it is water-intensive. In Chile's Atacama Desert, lithium mining consumes vast amounts of scarce groundwater, contributing to ecological stress. Cobalt is even more problematic. About 70% comes from the Democratic Republic of Congo, where reports of hazardous conditions and even child labor are widespread. That cobalt may end up in the battery of your phone or car. And then there's recycling, or the lack of it. Most lithium-ion batteries end up in landfills because recycling them is expensive and technically challenging. We're creating a growing mountain of electronic waste. The clean energy in your pocket isn't so clean once you follow the supply chain. So what's next? Scientists and companies are racing to invent safer, cheaper, longer-lasting batteries. Solid-state batteries replace the flammable liquid electrolyte with a solid one. They promise higher energy density and far greater safety, though costs remain high. Sodium-ion batteries use sodium instead of lithium. Sodium is abundant and cheap, found in ordinary salt, though the energy density is lower. Chinese and European firms are already piloting sodium-ion cells. Silicon anodes could store up to 10 times more lithium than graphite, enabling ultra-fast charging. The challenge is that silicon expands dramatically, cracking the electrode, but researchers are making progress. Grid-scale batteries go beyond lithium entirely, using flow batteries, iron-air chemistry, or other designs to store renewable energy at massive scales. The future of energy storage won't hinge on a single perfect material. It will be about mastering many elements, each optimized for different roles from your earbuds to your electric grid. Lithium-ion batteries transformed the modern world. They shrank electronics, revived electric cars, and enabled renewable energy. But they also introduced risks of fire, raised environmental costs, and tied our technology to scarce resources. The truth is, every battery is a compromise between energy, safety, cost, and sustainability. Lithium-ion struck a remarkable balance, but it's not the final word. So here's the big question. When future generations look back, will they see lithium-ion the way we see Edison's light bulb, brilliant, transformative, but only the beginning? One thing is certain. The story of batteries isn't over. It's just getting started. If you enjoyed this journey, hit subscribe. Because the next revolution in science and technology might be hiding in something just as ordinary looking as a little cylinder of black paste and foil.